Chapter 1. Expanded Introduction and Motion under Preservation. Introduction. This book develops a single structural claim, that difficulty, delay, irregularity, and undecided ability arise from the same source. They are not separate phenomena that merely resemble one another, nor are they artifacts of human limitation or incomplete knowledge. They are different expressions of a single constraint, the limited ability of a system to enforce preservation locally while advancing. The claim is intentionally narrow. It does not attempt to explain all forms of difficulty, nor does it promise methods for eliminating resistance. Instead, it seeks to explain why resistance appears where it does, why it persists despite effort, and why it often vanishes suddenly after structural change. The argument does not depend on psychology, intelligence, creativity, or strategy. It does not appeal to interpretation, metaphor, or narrative explanation. While examples will be concrete and familiar, the explanation itself is operational. Wherever a system advances, step by step, while attempting to preserve internal coherence, the same pattern appears. Motion begins smoothly. Resistance emerges. Exhaustion appears. Continuation halts or demands reorganization. These stages are not accidental, and they are not failures. They are signals. Specifically, they signal that preservation has become costly, that locality has been exhausted, and that coherence can no longer be maintained cheaply. The purpose of this text is not to eliminate difficulty, but to make it legible. Once difficulty is read correctly, much of what appears mysterious or paradoxical resolves into structure. Limits cease to threaten understanding. They become part of it. This reframing has practical consequences. When resistance is misread as failure, effort is misdirected. When it is read as structure, choices become clearer. One may reorganize representation, introduce new invariants, or stop without confusion. The framework does not prescribe which choice to make. It explains what each choice means. The book proceeds conservatively. No claim is introduced without grounding in a concrete process. No conclusion gestures beyond what the structure supports. Where motion stops, it stops deliberately. There are no promises of future resolution embedded in the argument. We begin with the simplest possible act of advancement, because it is there that the governing constraint appears in its most stripped-down form: motion and preservation. Counting is motion under constraint. At first glance, counting appears trivial. One enumerates objects or symbols and records a total. But this description conceals the essential feature of the act. Counting is not static description. It is stepwise advancement carried out under the requirement that each step remain compatible with what has already occurred. To count is to move forward while preserving agreement with prior steps. The act 4 is meaningful only because it preserves the structure established by 1, 2, and 3. If that structure is violated, the sequence may continue, but it no longer counts as counting. This requirement is not imposed externally. It is internal to the act itself. Without preservation, there is no notion of correctness, and therefore no notion of counting at all. Consider the act of counting aloud. If one says 1, 2, 4, the problem is not merely that a value was skipped. The problem is that preservation failed. The later step no longer agrees with the structure established earlier. Motion has continued, but coherence has not. Preservation must be enforced at each step. In simple counting, this enforcement is local. To move from one step to the next, the system need only know its current position and how to advance consistently. It does not need to inspect the entire history of the count. This locality is what makes counting cheap when it proceeds smoothly. Locality governs cost. As long as preservation can be enforced using nearby information, motion encounters no resistance. Each step requires minimal coordination. When locality fails, the system must consult more distant structure. Coordination expands. Delay appears. Delay is not inefficiency. It is the signal that preservation has become expensive. This becomes clearer when counting is modified by additional constraints. Consider counting while skipping certain values, or counting while maintaining two separate invariants simultaneously. As constraints accumulate, each step requires more coordination. Motion slows. Delay accumulates. Nothing has gone wrong. The system is paying the cost of coherence. Exhaustion is the terminal form of this signal. When preservation cannot be enforced even with expanded coordination, motion halts. The system refuses to proceed because continuation would violate internal consistency. This halt is not failure. It is integrity. A system that halts under exhaustion remains coherent. A system that continues without preservation collapses. This distinction matters. It separates systems that respect their own structure from systems that merely proceed. The former remain reliable. The latter do not. This pattern appears before abstraction. It does not depend on intelligence, intention, or interpretation. Any system that advances while preserving internal coherence encounters the same sequence: smooth motion, delay, exhaustion. Counting is merely the simplest place where this structure appears without disguise. Later sections will show that the same pattern governs verification, arithmetic, computation, and formal reasoning. But nothing essential is added by those contexts. They reveal, rather than later, the structure already present here. Chapter 2. Expanded verification and the cost of confirmation. Verification. Verification is motion viewed from rest. Where counting advances step by step, verification pauses and asks whether a claimed result could have been produced by coherent motion. This difference in orientation is essential. Counting accumulates context naturally as it proceeds. Verification must reconstruct that context without advancing through it. To verify a claim, a system must determine whether preservation could have been enforced throughout the hypothetical motion that produced it. When this can be done using local information, verification terminates quickly. When it cannot, verification must expand its scope. This expansion is not optional. It is demanded by coherence. Counting reveals constraint through delay. Verification reveals the same constraint through effort. These are not separate phenomena. They are the same preservation requirement experienced in different temporal orientations. Why verification feels harder? Construction often appears easier than verification. A result may be produced with little apparent difficulty, while confirming it afterward requires substantial work. This asymmetry is frequently misinterpreted as inefficiency or as a limitation of verification procedures. In fact, the asymmetry is structural. Construction benefits from temporal direction. Each step carries forward information about how preservation has been maintained. Decisions made earlier constrain later choices. Context accumulates automatically. Verification begins without that context. It is presented with a final state and must ask whether a coherent path exists that leads to it. This requires reconstructing compatibility across steps that are no longer present. Where reuse applies, verification collapses. If previously verified structure can be reused without rechecking, confirmation terminates early. This is why familiar results are easy to verify. Their preservation has already been encoded into representation, convention, or invariant. Where reuse fails, verification expands. Each failed attempt to confirm compatibility requires broader inspection. The system must consider additional dependencies. Work increases not because the claim is false, but because preservation cannot be enforced locally. This explains why proof length varies so widely. Short proofs are not short because they are superficial. They are short because reuse applies early. Long proofs are not verbose. They are exhaustive. Proof length measures how far verification must expand before preservation can be enforced. Watching verification fail. Consider verifying a simple arithmetic computation performed by an unfamiliar method. Even if the result is correct, Confirmation may require reconstructing each intermediate step because no reusable structure is recognized. Now consider verifying a result produced by a well-known algorithm. The same numeric outcome may be confirmed almost immediately because the algorithm itself encodes preservation. Reuse applies. The difference lies not in truth but in structure. Verification fails exactly where counting would have stalled. Where motion cannot proceed without violating coherence, confirmation cannot terminate without exhaustive reconstruction. The two experiences differ only in orientation, not in constraint. This equivalence is central. It explains why verification cannot, in general, be made arbitrarily cheap. It also explains why improvements in representation can cause dramatic collapses in verification cost. What changes is not the truth of claims, but the location of the horizon. Chapter 3. Expanded reuse, difficulty, and horizon formation. Reuse as preserved work. Reuse is preserved work. Whenever prior structure can be applied without rechecking, preservation collapses into representation. Motion accelerates. Verification terminates early. What once required effort becomes trivial because the work has already been enforced and encoded. Reuse is not convenience. It is structure. A reused component carries a guarantee that its internal preservation has already been enforced. The system is relieved of the burden of re-verifying that structure each time it appears. This is what allows large systems to function at all. Without reuse, every task would require full reconstruction. Motion would be prohibitively expensive. Preservation would exhaust itself almost immediately. Reuse in practice. Consider long addition performed by hand. The procedure works because carries preserve local consistency. Each column can be processed independently, except where a carry propagates. Most steps reuse the same local rule. Verification collapses because the structure of the algorithm enforces preservation. Now remove reuse. Imagine recomputing each digit without trusting the carry rule. Each step would require consulting the entire prefix. The procedure would become infeasible. Nothing about the arithmetic has changed. Only reuse has been withdrawn. This pattern appears everywhere. Programming languages rely on reusable abstractions. Mathematics relies on lemmas. Institutions rely on procedures. Reasoning relies on conventions. Where reuse applies, work collapses. Where reuse fails, work expands. Difficulty. As structural cost. Difficulty increases exactly as reuse decreases. This relationship is not psychological. It does not depend on intelligence, experience, or effort. It depends only on whether preservation can be enforced locally using existing structure. A problem is difficult relative to a representation because preservation cannot be enforced locally within it. Change the representation and difficulty changes. Introduce reuse and difficulty collapses. Remove reuse and difficulty explodes. This explains why difficulty is uneven across domains and across time. Problems that resisted all effort for years may suddenly become trivial after a single structural insight. The effort was not missing. The structure was. Horizon formation. A horizon marks the boundary beyond which reuse no longer applies. Within a horizon, preservation is local and motion is cheap. At the horizon, preservation becomes expensive. Beyond it, preservation cannot be enforced without extension. Difficulty is the experiential signal of proximity to a horizon. Persistent effort without local progress is not personal failure. It is the experience of operating at a boundary where reuse has been exhausted. This recognition alters interpretation. Resistance is not opposition, it is information. It tells the system where structure ends and where extension would be required. It distinguishes regions where persistence is productive from regions where reorganization is necessary. Reading difficulty correctly. When difficulty is misread, effort is misdirected. Systems attempt to push through boundaries that cannot be crossed without new structure. Exhaustion accumulates without progress. When difficulty is read structurally, choices become visible. One may extend the representation. One may introduce new invariants. One may halt without confusion. The framework does not dictate which choice to make. It clarifies what each choice entails. Chapter 4. Expanded arithmetic as a case study in preservation. Why arithmetic? Arithmetic exposes preservation constraints with unusual clarity. Its representations are explicit. Its operations are unforgiving. Its failures cannot be softened by interpretation. For this reason, arithmetic provides a controlled environment in which to observe how preservation, reuse, delay, and exhaustion interact. What appears here in a simple form reappears, often disguised, in more complex systems. Equality. Consider equality verification. To verify that two numerals represent the same quantity, a system aligns their representations and checks local consistency. If the symbols match position by position, verification collapses immediately. No global coordination is required. No reconstruction of history is required. Equality permits total reuse. The representation itself carries preservation. Once alignment is confirmed, nothing further must be checked. This is why equality tests are cheap across nearly all computational and mathematical contexts. Order. Order introduces partial reuse. To verify that one number is greater than another, the system compares representations until a decisive difference appears. In most cases, this difference appears early. Verification terminates locally. Worst-case behavior exists only when long prefixes agree. Even then, verification cost is bounded by representation length. Order, therefore, has a shallow horizon. Divisibility. Divisibility introduces conditional reuse. To verify that one number divides another, the system must determine whether a consistent grouping exists. Some instances align quickly and collapse. Others require extended exploration. Preservation applies only when structure aligns. Where alignment fails, verification expands. This variability explains why divisibility tests range from trivial to costly, depending on instance. Primality. Optimality removes reuse almost entirely. To verify that a number has no non-trivial divisors, the system must rule out all possible groupings. No early witness certifies success. Every candidate alignment fails locally. Verification expands repeatedly until exhaustion or termination by proof. This difficulty is not accidental. It is structural. The hierarchy. These cases form a strict hierarchy. Equality permits total reuse. Order permits partial reuse. Divisibility permits conditional reuse. Optimality permits none. Difficulty increases precisely where reuse disappears. This is not a property of numbers. It is a property of preservation under representation. Watching failure. Consider attempting to verify primality by trial division without recognizing structure. Each failed divisor provides local information but no global progress. Verification expands uniformly. Exhaustion is inevitable. Now introduce structure. Recognizing symmetry, bounding, or special forms introduces reuse. Verification collapses in regions where it previously expanded. The horizon shifts. Nothing about the numbers has changed. Only preservation has. Generalization. Arithmetic does not create these constraints, it reveals them. The same pattern will appear wherever verification depends on alignment, reuse, and local enforcement. Arithmetic simply makes the boundary visible. Chapter 5. Expanded computation and the cost of coherence. Computation as preserved motion. Computation is structured motion under invariance. A computation advances through a sequence of states while attempting to preserve conditions that define correctness. These conditions may be explicit, such as program invariance, or implicit, such as consistency of representation. As long as preservation can be enforced locally, computation proceeds smoothly. Each transition depends only on nearby state. Verification collapses because the rules of transition already encode preservation. When local enforcement fails, coordination expands. A step that depends on distant state requires inspection, synchronization, or reconstruction. Cost increases, delay appears. The system must work harder not because it is inefficient, but because preservation has become expensive. This behavior is not accidental. It is the cost of coherence. Termination and divergence. A computation that permits reuse terminates locally. Reusable subroutines, memorized results, and stable invariants allow work to be preserved across steps. Once a region of the state space has been verified, it need not be re-verified. Motion accelerates. A computation that requires global coordination expands. When each step depends on interactions across the entire state, preservation cannot collapse locally. Verification expands repeatedly. Exhaustion threatens. A computation that cannot enforce preservation locally does not terminate. This is not a defect of machines. It is a structural consequence of unbounded coordination. Programs halt when preservation stabilizes. They diverge when it does not. Why speed does not help. It is tempting to believe that faster machines, parallel execution, or clever optimization can eliminate divergence. They cannot. Speed changes how quickly a horizon is reached. Parallelism redistributes coordination. Optimization compresses constant factors. None of these alter whether preservation can be enforced locally. Only structure changes that. This explains why undecided ability persists under all acceleration. The halting problem is not mysterious. Determining whether an arbitrary program halts would require enforcing preservation across unbounded execution without performing that execution. Local verification cannot suffice. The system halts not because truth is absent, but because coherence cannot be guaranteed locally. Inheriting arithmetic. Computation does not escape arithmetic, it inherits its constraints. Carries become state dependencies. Alignment becomes synchronization. Exhaustion becomes divergence. The surface differs. The structure does not. Chapter 6. Expanded complexity as horizon pressure. Complexity reframed. Complexity is not an intrinsic property of problems. It is a measure of how far verification must expand before preservation can be enforced. Where preservation is local, complexity is low. Where preservation requires broad coordination, complexity grows. This reframing removes a common misconception. Difficulty is often attributed to size, randomness, or lack of cleverness. In reality, difficulty reflects the absence of reusable structure within the chosen representation. The same task can be trivial or intractable depending entirely on how preservation is encoded. Representation and cost. A representation determines which invariants are explicit and which must be reconstructed. When invariants are explicit, verification collapses. When they are implicit or absent, verification expands. This explains why reformulating a problem can change its complexity class without altering its underlying content. The structure has changed, not the truth of the problem. Asymptotic complexity classes persist because they capture preservation limits that survive representation changes. They do not measure effort in the abstract. They measure coordination costs that cannot be eliminated without new structure. Collapse and explosion. Complexity collapses when reuse appears. When a representation introduces invariants that allow verification to terminate locally, previously hard problems become easy. This collapse often feels sudden, as if a barrier has been removed. In fact, the horizon has shifted. Complexity explodes when reuse fails. When invariants do not align, verification must consider many interacting dependencies. No local shortcut applies. Exhaustion appears. This explains why heuristic methods succeed locally but fails globally. Heuristics exploit structure that applies within a limited region. They extend locality temporarily. When the region ends, the horizon reappears. Formal complexity. Complexity theory formalizes these boundaries. Lower bounds identify regions where no representation has yet been found that allows preservation to collapse locally. Reductions show that different problems share the same horizon structure. These results do not prove impossibility. They locate limits. The question of P versus NP. The question of whether P equals NP is therefore operational. It asks whether a representation exists that allows verification to collapse locally for problems currently requiring global coordination. If such a representation exists, the horizon shifts. If not, exhaustion remains. Either outcome preserves the framework. Complexity theory does not ask whether problems are hard. It asks where preservation fails. Chapter 7. Expanded undecidability as a boundary of preservation. Undecidability revisited. Undecidability arises at the same boundary encountered throughout this work. A statement is undecidable when verification would require unbounded expansion. No finite local method suffices. The system halts not because truth is absent, but because preservation cannot be enforced without extension. This distinction is essential. Undecidability is often framed as a paradox or a failure of formal systems. In reality, it is evidence that the system is behaving coherently. It refuses to assert what it cannot preserve. Undecidability and incompleteness are therefore not pathologies. They are horizon statements. They identify exact boundaries beyond which preservation cannot be enforced without changing the system itself. Why extension does not remove limits. Extending a system introduces new preserved structure. It allows verification to collapse in regions where it previously expanded. Statements that were once undecidable become decidable under the new framework. But extension does not remove horizons. New undecidable statements arise precisely where reuse again exhausts itself. This is not regression. It is the cost of coherence under growth. This pattern explains why foundational limits persist across generations of formal systems. Each extension resolves some boundaries while introducing others. The horizon shifts outward, but it never disappears. Misreading undecidability. Undecidable statements are often treated as meaningless or unanswerable. This is a mistake. They are meaningful precisely because they identify the limits of preservation. They reveal where structure ends and where additional commitment would be required. Attempts to eliminate undecidability without extension fail because they attempt to force preservation where it cannot be enforced. The same exhaustion reappears in altered form. Recognizing the boundary clarifies what kind of progress is possible. Some questions can be relocated. Some can be resolved by extension. Some must remain undecidable within the current framework. This is not a limitation of inquiry. It is its structure. Foundational consequences. Seen through this lens, undecidability is not a threat to mathematics. It is a guarantee of integrity. A system that asserted answers beyond its preservation capacity would not be stronger. It would be incoherent. The refusal to decide is an act of fidelity, not weakness. This perspective dissolves much of the anxiety surrounding incompleteness. The limits are not arbitrary, they are necessary. Chapter 8. Expanded randomness, irregularity, and compression failure. Randomness as a diagnostic. Randomness is often treated as a primitive explanation. When behavior resists prediction or compression, it is labeled random, and analysis stops. This move is understandable, but it obscures structure. In most cases, randomness is not a generator of behavior. It is a diagnostic, a signal that structure exists but cannot be locally enforced within the current representation. Randomness names compression failure. A sequence is described as random when no shorter description reproduces it within the system's representational constraints. This does not imply absence of structure. It implies absence of reusable structure recognizable to that system. Randomness is therefore relative. A sequence may be incompressible relative to one encoding and trivial relative to another. Changing representation introduces reuse and shifts the horizon. What appeared random becomes structured once preservation can be enforced locally. Determinism and appearance. Deterministic systems routinely produce behavior that appears random under local observation. This is not paradoxical. Local observation lacks access to the full structure governing the system. Preservation may be enforced globally, but not locally. The observer experiences irregularity because reuse fails at the observed scale. This explains why chaotic systems exhibit sensitivity without indeterminacy. Small differences propagate because preservation requires coordination across many interacting components. Verification expands rapidly. Prediction fails not because the system is random, but because locality has been exhausted. Compression algorithms. Compression algorithms make this relationship concrete. A dataset is incompressible when no compression scheme reduces its size. This does not mean the data lacks structure. It means the scheme cannot recognize or reuse the structure that exists. Better compression requires better invariance, not more computation. Probability often enters at this point. Probability summarizes frequency where position is inaccessible. It replaces local verification with global averaging. This is useful, but it does not create reuse. It does not shift horizons. It smooths them. Probability does not abolish exhaustion. It manages it. Irregularity. As experience, irregularity is not error. It marks regions where preservation applies unevenly. Local patterns may exist, but they do not align in a way that permits global reuse. Verification must expand repeatedly. Delay persists. Irregularity is the experiential signature of operating near a horizon. Recognizing this prevents misinterpretation. Where irregularity is treated as noise, structure is overlooked. Where it is treated as randomness, extension is discouraged. Read correctly, irregularity is informative. It identifies where preservation fails and where extension would be required. The role of randomness. Randomness should therefore be used sparingly. It is not an explanation. It is a boundary marker. Used correctly, it tells the investigator where the representation has reached its limit. Used incorrectly, it halts inquiry prematurely. This reframing restores meaning to irregularity. It ceases to threaten order. It becomes evidence of structure just beyond reach. Chapter 9. Expanded asymptotic law, scale, and the limits of summary. Why asymptotic exist? Asymptotic descriptions arise when direct positional verification becomes impractical. When a system advances far enough, enforcing preservation at every individual position becomes prohibitively expensive. Rather than tracking exact motion, the system relocates description. It summarizes behavior over large regions, trading positional fidelity for stability. This is not approximation in the usual sense. It is relocation of enforcement. Asymptotic laws allow preservation to be enforced at scale when local verification cannot be maintained. They do so by discarding position and retaining frequency, trend, or average behavior. What asymptotic preserve? Asymptotic reasoning preserves relationships, not instances. It answers questions about density, growth rate, and distribution rather than about specific positions. This shift explains both the power and the limits of asymptotic laws. They succeed exactly where individual verification fails. They fail exactly where individual structure matters. This is not contradiction. It is domain separation. Local failure, global order. At small scales, behavior often appears irregular. Verification of individual cases expands and exhausts. Delay accumulates. Motion stalls. This experience leads naturally to the belief that the system is chaotic or unpredictable. At large scales, behavior appears smooth. Aggregate properties stabilize. Laws emerge. Predictive power returns. This does not eliminate local irregularity. It bypasses it. Both descriptions are correct within their horizons. The error arises when one is mistaken for the other. Prime numbers. As an example, prime number theory illustrates this distinction clearly. At local scales, prime gaps appear erratic. Verification of individual primality requires exhaustive effort. No local shortcut applies in general. At global scales, density laws describe the distribution of primes with remarkable accuracy. These laws do not identify individual primes. They summarize frequency. The asymptotic description does not predict specific primes. The local description does not deny density. Each respects its boundary. Confusion and misapplication. Confusion arises when asymptotic results are treated as if they applied locally. Predictions are made about individual behavior based on average trends. When these predictions fail, the asymptotic framework is blamed. This misreads its purpose. Asymptotic were never meant to enforce preservation locally. They exist precisely because local enforcement is impossible. The cost of scale. Scale does not eliminate difficulty. It redistributes it. Asymptotic laws make large-scale reasoning possible at the cost of positional detail. This trade-off is not optional. It is structural. Any attempt to reason globally without paying this cost encounters exhaustion. Any attempt to apply global summaries locally encounters error. Understanding the trade-off. Seen correctly, asymptotic reasoning is neither superior nor inferior to local analysis. It is appropriate where preservation can be enforced at scale. It is inappropriate where position matters. Recognizing this prevents false expectations. Asymptotic are not promises. They are agreements. They agree to ignore what cannot be preserved locally in exchange for stability where preservation remains possible. Chapter 10. Expanded extension, failure, and orientation. Extension as structural change. Extension introduces new preserved structure. It does not remove limits. It relocates them. When a system is extended, it gains new invariants that allow preservation to be enforced locally in regions where it previously expanded. Verification collapses in those regions. Motion accelerates. Results that once required exhaustive effort become trivial. This change often feels dramatic. Problems that resisted all effort suddenly yield. The effort was not missing. The structure was. But extension is not free. Each new invariant introduces new obligations. Preservation must now be enforced with respect to a richer structure. Horizons shift outward, but they do not disappear. New boundaries appear where reuse again exhausts itself. This recurrence is not failure. It is the cost of coherence under growth. True and false extension. Not all extension is structural. Some extensions introduce new notation, vocabulary, or decoration without adding reusable preservation. These changes may redistribute difficulty without reducing it. Exhaustion reappears elsewhere. True extension reduces verification cost. False extension relocates it. Distinguishing between the two requires attention to reuse. If new structure allows verification to terminate locally where it previously expanded, extension has occurred. If verification still expands uniformly, structure has not been added regardless of surface complexity. Failure as signal. Failure is horizon encounter. A system that halts when preservation fails remains coherent. A system that proceeds without preservation collapses. This distinction applies beyond formal systems. Institutions that respect their own constraints halt when coherence cannot be maintained. Institutions that ignore constraint proceed incoherently and lose reliability. The same pattern governs reasoning, computation, and organization. Stopping is not surrender. It is fidelity. Halt conditions. Halt conditions are not defects. They are safeguards that protect coherence. A system without halt conditions would continue indefinitely without preserving meaning. Such continuation would not be strength, it would be noise. Recognizing halt conditions as structural clarifies their role. They mark the precise points where extension would be required to proceed coherently. Orientation. This framework does not solve problems. It locates them. It explains why difficulty appears where it does. It explains why limits persist. It explains why progress is discontinuous. Beyond this point lie only three options: extension, reorganization, or stopping. The framework does not prescribe which option to choose. It clarifies what each entails. Oriented stopping. Stopping, within this framework, is precise. To stop is to recognize that preservation can no longer be enforced without extension. To continue without extension would be incoherent. To extend without necessity would obscure the boundary rather than clarify it. A correct stopping point is therefore structural. It occurs exactly where the explanatory mechanism ceases to evolve. That point has now been reached. Chapter 11. Expanded integration, synthesis, and reader orientation. Integration without extension. At this stage, the framework has been fully articulated. No new mechanisms are introduced in this section. Its purpose is integration, to make explicit the relationships among concepts that have already appeared and to stabilize the reader's orientation before the argument concludes. Throughout the preceding chapters, the same constraint has been observed under different representations. Preservation must be enforced locally for motion to remain coherent. Where it can be enforced, motion is cheap. Where it cannot, delay appears. Where delay cannot be resolved, exhaustion halts progress. This pattern has governed counting, verification, arithmetic, computation, complexity, randomness, asymptotic reasoning, and undecidability. These domains differ in surface features only. Structurally, they share the same boundary. What appears as difficulty in one domain appears as undecidability in another. What appears as randomness in one context appears as compression failure in another. These are not separate phenomena. They are distinct manifestations of the same preservation limit. Synthesis of key relationships. Several dualities now stand clearly in view. Counting and verification are the same process viewed in opposite temporal directions. Reuse and difficulty are inversely related. Horizons mark the exhaustion of reuse. Extension shifts horizons without eliminating them. None of these relationships depend on domain-specific assumptions. They arise wherever a system attempts to advance while preserving coherence. This universality is not metaphysical. It is operational. No appeal to psychology, probability, or interpretation is required. The framework describes how systems behave when coherence matters, regardless of their implementation. Why the argument stops here? It is natural to ask whether the framework can be pushed further. The answer depends on what further means. If it means introducing additional domains, examples, or applications, the framework already applies. Such extensions would add illustration, not mechanism. If it means introducing new explanatory principles, the framework resists. Every attempt to extend explanation beyond preservation and locality reduces to relabeling or metaphor. This resistance is not limitation. It is closure. Closure occurs when the explanatory mechanism ceases to evolve under expansion that condition has now been met. Reader orientation. The value of the framework lies not in what it predicts, but in how it orients. It changes how difficulty is interpreted. It changes how delay is read. It changes how limits are understood. Difficulty ceases to be a personal failure. It becomes a structural signal. Irregularity ceases to be noise. It becomes evidence of boundary. Exhaustion ceases to be discouraging. It becomes informative. This reorientation does not eliminate difficulty. It makes it legible. With legibility comes choice. One may extend representation. One may reorganize structure. One may stop without confusion. What one may not do coherently is pretend the boundary is not there, the role of the reader. This framework does not instruct action. It equips diagnosis. The reader remains responsible for deciding how to respond to a horizon once it is encountered. The framework clarifies what is at stake in that decision, but it does not dictate outcomes. In this sense, the work is deliberately incomplete. It stops where explanation ends and responsibility begins. Afterword. This work is complete as written. Any further expansion would consist of application or illustration rather than explanation.